Okay, thank you so much for joining me in this part 2 of our short circuit studies series. In part 1, we simplified our network into this impedance diagram where we represented each equipment in its equivalent impedance at a new base. So in this video, we use the same impedance diagram now to compute the total impedance between the voltage source and the faulted point in our network so that we can compute the fault current. And as we do these calculations, you see the significance of the statement, that is between the voltage source and the faulted point. After doing the head calculations, we'll then model this network in ETAP, run a short circuit study to confirm our hand calculations. So let's dive right into it. Now, this is our network from the last video, our impedance diagram. So we want to compute the fault current at bus B, which is our unit bus or our unit bus in unit bus A. And this is a 6.6 kV rated bus. Right. So you could just go right into it and just formulate the equation for this whole network. But I wanted us to take it step by step, just like how I did to confirm my hand calculations in the ETAP model. So let's start off simple. We will just consider just these three equipment in fault bus B1. Let's see then what is the fault current, or what is the magnitude of the fault current when we fault bus B1, when we have our utility grid, our generator transformer, and the generator itself. So then what will be the total impedance between the voltage source and the faulted point? That will be the impedance of our generator in parallel with the series combination of our utility grid and our generator transformer. So that will be, what is the impedance of our generator? It's given there, it's 0.0074133 plus J 0.0741333. This will be in parallel with the series combination of our utility grid, which is the impedance of the utility grid 0.002855.977 plus J 0.099959208. This will be in series with the impedance of our generator transformer, which is 0.004267958 plus J 0.068287808. This is the full equation for our total impedance between the voltage source and the fault current. The voltage source will be the utility grid in this case. So what is that? When you compute this, these are complex numbers, you know how to deal with them in parallel, so forth. So when you compute this, you should get the entire thing should give you 0.0042362758 plus J 0.051495441. This is in rectangular form. Now in polar form, this will be, and this will help us get the magnitude of our impedance. That will be 0.051669402 and an angle 85.30 degrees. So the magnitude of our impedance is 0.051669402. So then now that we have the total impedance, how do we compute our fault current at bus B1 in this scenario? Well, we'll then use this formula. So the voltage fault will be our base MVA, which is 100 divided by √3 multiplied by the voltage of the bus. And the voltage of the bus that we are faulting is this, even if you check in our last video, this is the 15.75 kV bus. You multiply that by the magnitude of the total impedance, which we calculated just now, and that is 0.05166 and the rest of it. So that should give you the fault current, and that when you compute that, it should give you 70.946 kiloamps. So this is the magnitude of the fault current at bus B1 when we have these three equipment. Now let's jump into ETAP, model this scenario, and then confirm our hand calculations. Now, this is our model in ETAP, okay? There's the entire network, but for now, we'll focus on just the three equipment that we just analyzed. That is our utility grid, our generator transformer, and our unit generator. So for now, I'll disconnect the rest of the downstream equipment so that we can focus on these three. Our utility grid, there's the 1000 MVA utility grid. It's a 400 kV utility grid. Short circuit rating is 1000 MVA. The X/over ratio, like we saw in the last video, was provided. It's 35. Then ETAP calculates the KA for you, or the symmetric short circuit current for you. And then this is what we had to calculate in our last video. The short circuit impedance at the base 100 MVA. These are in percentage, and these are equivalent to the per unit that we calculated in our last video. So these I had to manually enter. So I just focus on the positive sequence, and then it calculated the rest of the negative and zero sequence. So that is that with our utility grid. Our generator transformer, same as this, I had to enter these ratings: 400 primary rating, 50.75 secondary winding rating. It's 190 MVA. This is data that I had to manually enter given our specifics from the last video. And the impedance rating, this X/R, this percentage impedance is a manually entered. These are not typical impedance or X/R values. These are manually entered, right? And then there's the positive sequence resistance in percent and the positive sequence reactance in percent. So these were manually, of course, these ETAP calculates them for you, right? And then the same as our generator. The point is, these are manually connected. These are not typical data. So all of these ratings of the generator and then the impedance model entered these. Now, let's run a short circuit study and see what ETAP gives us. So let me check if there are any faulted buses. The short circuit study case, there's nothing. So I will then fault bus B1 because this is the analysis that we just did with our hand calculations. So I'll fault this and then run the device due to run my short circuit study. Mind you, in our calculations, we got 70.946, and there we have it, 70.946. So our hand calculations match our ETAP results. Now, something to highlight, you may have noticed that the positive sequence resistance in percentage is nowhere equal to what we use in our calculations. Same applies to the positive sequence reactance. They are nowhere equal to what we use in our calculations. So is it a coincidence that we use these values and got the same answer? And there's the answer to that. When we generate our short circuit report, and you look at the branch impedances, let's see what ETAP used to compute this fault current. So we have it here, just generated. Now look at, let me explain this a bit. So look at what ETAP used. These are the values that we computed, that we use in our hand calculations. And this is the whole essence of our previous video of why you wanted to calculate everything at a new base, because this is what ETAP uses in its calculations. So the values that we saw here are at the equipment base. So these are at the base 190 MVA by virtue of this machine being a 190 MVA transformer. So that's something to note. Also, because I wanted to make a direct comparison between my hand calculations and the results, I had to remove all default adjustments in my social study, things like impedance tolerance. And to see how that could have affected our results, I'll just show you the help section helps us understand what effect this could have. For instance, if I had not removed the transformer impedance tolerance, this is what it would have done. It would have resulting in a higher fault current than what probably we have computed. But because I wanted to have a direct comparison, I removed all these adjustments that the ETAP by default, or in most cases, comes with. That's something to note when using this tool. So yes, our hand calculations match our ETAP results. So we'll go back to our calculations and consider another scenario. Okay. Now, let's take another scenario. Let's add another equipment downstream. That is our unit generator. What would then be the fault current magnitude at bus B2 when we have the utility grid, the generator transformer, and the generator, as well as the unit generator, the unit transformer? So the total impedance between the voltage source and the faulted point at B2 would be the impedance of our generator parallel to the series combination of a utility grid and the generator transformer. Then all these will be in series with the unit transformer. Now, this parallel series combination is a bit of a skill. It might be uncomfortable for a first timer, but we get the hang of it with time. So that will be, mind you, this we had already computed or calculated in our previous step. So that will be 0.0042 362758 plus J 0.05149 54481. So this will be in series with the impedance of our unit generator, which is 0.032496057 plus J 0.38995268. Now, when you calculate that, it should give you 0.036732 plus J 0.441448136. In polar, for us to get the magnitude, we'll convert this rectangular impedance to the polar, and that will be 0.442973724 at an angle 85.24 degrees. So now that we have our magnitude of our impedance between the voltage source and the faulted point, what would then be our fault current at B2? That will be our MVA, our base MVA, divided by square root 3 multiplied by the voltage of the bus. This is a 6.6 kV bus. That will be 6.6 kV multiplied by the magnitude of our total impedance between the voltage source and the faulted point. So that will be, if you calculate that, it should give you 19.748 kiloamps. So this is the fault current a bus B2 when we have these four equipment: our utility grid, generator transformer, unit transformer, and our unit generator. So let's jump to ETAP and simulate or perform a short circuit study with this particular scenario. All right. So I will connect my HV unit transformer, and then disconnect the rest of the downstream equipment. In fact, I should have just done this because we are 14 bus B2. So I'll remove these cables and everything downstream. Then I'll go back to my short circuit study mode. Okay, so now we have this in our analysis. Now I'll remove this fault, and either way, even if I had left bus B1 faulted, it would not affect my results when I fault bus B2. And I think this is really smart because ETAP doesn't take those as occurring at the same time. Okay, it takes this two independent scenarios. Okay, so I faulted bus B2. We'll run the short circuit study. Mind you, our hand calculations gave us 19.748, and that is what we have here. The fault current at bus B2 is 19.748. So our hand calculations match our ETAP results. So we'll go back to our calculations and then take another scenario. Right. So that's the 19.748 that we confirmed in an ETAP. Now let's take the last scenario before we compute the entire impedance of the entire network. Let us assume that a fault occurs at bus B3, which is our unit board A, a 6.6 kV rated bus. So what would then be the total impedance between the voltage source and the faulted point? Now, I want you to notice something. When you look at this network here, is there a voltage source between it and bus B3? No. So because of that, we will not include this in our analysis. So our transformer, in a sense, is unloaded. Now, if there were a static load connected to the transformer, you would still not include this in our calculation because it will not contribute to the fault current contribution in bus B3. However, if it had an induction motor or a generator, even if they were running unloaded, we would still include those in our analysis because that would be a voltage source behind an impedance. That's why I said it's important that we understand the statement of what impedance to consider. Impedance between the voltage source and the faulted point in our network. So in our analysis, we will not include the branch that I just circled in red. So then what is our total impedance between the voltage source and the faulted point? That will be the series combination of cable 3 and our feed motor pump or motor 1. All this will be in parallel with the rest of the network. So that will be the impedance of our generator parallel to the impedance of our generator parallel to the series combination of our utility grid and the generator transformer. All these are in series with our unit transformer. And then these would then be in series with the impedance of cable 1. So this will be the formula or the equation that will compute the total impedance between the voltage source and the faulted point. So what are these values? So the series combination of our cable 3 and our feed motor pump will be, we have 0.0131 plus J, 0.005069,635, plus 0.02211, 98574 plus J, 7.211073516. So that's the series combination of these two. All of this will be in parallel with the rest of the network. And that will be the impedance of our generator. The impedance of our generator, as calculated earlier, is 0.00741133 plus J 0.0741, right? So this will be in parallel with the series combination of our utility grid and our unit, our generator transformer. So the impedance of our utility grid will be, or is, as you see from my impedance diagram, that is 0.002855977 plus J 0.099959208. So this with the impedance of our generator transformer, that is 0.004267958 plus J 0.068287808. Then, so we are done with this. Now, we will then, all that will be in series with our unit transformer, the impedance of our unit transformer, and that is 0.032496057 plus J 0.389952,688. And then all that, in fact, start with this curly bracket, and then all that will be in series with the impedance of our cable 1. So that is 0.0131 plus J 0.005069,635. And that will be our entire equation. So, oops. Okay, that for Right. So this here is our entire equation. So when you solve that, it should give you So the series combination of our cable 3 and our feed motor pump should give you 0.234299,278 plus J 7.216143,151. And then all this is in parallel with the entire network, the impedance of the entire network, and that is 0.049833036 plus J 0.44651 7771. And that will give you 0.44, actually 0.044. One mistake with these numbers, it just destroys everything. So you might also want to be careful with that. So 0.0449847,578 plus J 0.4206426,419. Now in polar form, for us to get the magnitude of our impedance, that is 0.423,041,203 angle 83.89 degrees. Okay. And then we can compute our fault current. Our fault current would then be our MVA base, our base MVA divided by square root 3 multiplied by the voltage, that is 6.6, multiplied by the magnitude of our impedance is 0.423, 0.423, doesn't look like 0.423, and the rest of it. That will give you a fault current of 20.678 kiloohms. That is that with this part of our network. So we'll jump to ETAP, no matter the scenario, to confirm our hand calculation before now we finally consider the entire network of our generating unit. Okay, so back at ETAP, now we'll connect the rest of our network. Mind you, we only, in our analysis for now, we only considered this part of our network, except from cable C2 and on the right side. So I will just reconnect this part because that is what we are interested in for now. So now, because we have a number of new equipment, I'll just highlight how I modeled it. This is our cable. You remember this cable 1 up until cable 6. These are 50-meter long. I didn't do anything here. Impedance. Now, this is where, if you want, I created my own Excel sheet where I have all these values. So there's the default one that comes with ETAP, the cable Z external file. So I edited that, modified it, and created my own Excel sheet. I think I might be able to show you. Let me see something. I can show you what that looks like. In just a second. Okay, so this is how it looks like. That's what I only changed. I only focus on the fundamental frequencies. So these are what, and let me show you some. So I just modified the the positive sequence resistance, and this, if you look carefully, this is the 2 pi FL, X, the rate is equal to 2 pi FL. So that is basically the formula that's been applied here. So that's what I did. I just had to edit this and then edit it my positive sequence resistance in the negative sequence. So that's what I did to specify um, the impedance, to specify the impedance of my cable, or what I'll use in my cable. Okay. Or if you want to keep it simple, you can just use the library and then manually edit your impedance here. So, but I just decided to I'll just go with this. So that's how I modeled this positive sequence resistance for my own per kilometer, my own per unit length. And so that's what I did also. Um, yeah, so that is what I did. This is ohms per kilometer. So that's what I did for the cable. So also the feed motor pump, all these are manually edited in, as well as the impedance. These were as per the specifications as stated in our previous video before we simplified the entire network into an impedance diagram. Right, so that is that. By the way, these tie or coupling breakers are open because that's what I wanted to analyze for this scenario. So if I wanted to close, I would have now had to compute um, new calculations particular for that scenario, right? So we connected the part that we have just been analyzing the hand calculation. So we'll then go to a short circuit mode, forward this bus, and then run our short circuit study. I will remove this fault just to keep it simple, but like I said, it doesn't affect anything. So remember, our calculations gave us 20.678. So we'll run the short circuit study and then see how much we get. And there we go, 20.678. And like I said, this branch does not contribute anything does not contribute to the forward current at this bus. Why? Because our transformer is unloaded. There's no voltage source behind the impedance by this branch. Hence why we can see there's nothing being contributed by this branch. Okay. So again, our hand calculation will match our ETAP results. Now we'll go back to our calculations and consider the last scenario, which is now how we calculate the impedance now of the total of the entire network of our generating unit. So now we are here. What would then be the total impedance towards bus B3 when we forward that unit board A? So then what would be the total impedance? Okay, so how will we compute that? Again, we have the series combination of cable 3 and a feed motor pump parallel to the entire network, right? So parallel to the entire network. So just to break it down, this this the series combination of cable 3 will be in parallel to the rest of the network. So I'll just try to make it easy to see by using, so this will be in parallel to the rest of the network. And what is the rest of the network? This is the rest of the network. Everything from here. Again, we will not consider the branch with the transformer because it is also unloaded. So this will be the rest of the network. So it is in parallel with the rest of the network. Okay, so and what is that? So that will be, we'll start off with our cable 6. So we have the series combination of cable 6 and our condensate pump motor or motor 2. This is in series with cable 2, the impedance of cable 2, and then that all this is in parallel with everything upstream of or everything upstream of bus B2. So that is, it is in series with, the impedance of our generator being parallel to the series combination of our utility grid and our generator transformer. And then all of that being in series with our utility, our unit transformer. So all this being in series with our unit generator, right? And then all that so this is that. And then we see, because that is generator being parallel with that, and then this. Okay. And then this, all of this, so this bracket is the bracket. So all this will be in series with cable 1. Let's see, let's confirm again. So we have that. Okay, so that's how it will be. Okay, so this is the entire equation that will help us calculate the total impedance between the voltage source and the faulted point in our network. So that will be, there's a lot of brackets, so we just need to be very careful with how we use them. Okay, just a second to confirm everything again. Okay, we have the series combination of cable 6 and motor number 2, which is our condensate pump, and that is in series with cable 2. So that entire network is parallel with the rest of everything, like I said. So that will be this. The generator being parallel to the series combination of the utility and the generator transformer. It's okay. In series with our unit generator, and then all that parallel with everything we just considered. Actually, it should be parallel, not series. Okay, so we corrected. So now that should be fine. Okay, now The series combination of cable 3 and our feed motor pump is that should give us 0.234299,278 plus J 7.216143151. All this is in series with the rest of the network. We'll just use a different color just to make it stand out. So that is what we have here. We have so this the series combination of cable 6 and motor 2 will be, when you calculate that, it should give you 1.62945104 plus J 34.19087938, and that is in series with the impedance of cable 2, which is 0.013100704 plus J 0.051, actually 5069635. Right, so that will be that with this, and then that is in parallel with the series connection of our the series connection of, so this here we calculated it on our previous steps, so all that will give us 0.0042 actually that will give us, just a second, yes, we calculated as our previous step, so that should be 0.0423627221455 plus J 0.0514954429544, right? And then so actually this is the entirety of this, and then that will be in series with the impedance of cable 1. So this will be in series with the impedance of cable 1, which is 0.0131007 plus J 0.0050696063635. And that would be it. Actually, no. It. In fact, the rest of the equipment, the rest of the model is what is in series with cable 1. Okay, sorry about that. Rest of the model in series with cable 1. Am I confusing that? So that should be this, yes. Sorry about that. That's what happens when there's a lot of brackets. So that is that. Because like I said, this or the orange part is in parallel with the series combination of motor of cable 3 and motor 1 or feed motor pump. So this is how it should be. Okay. So when you compute that, all of it should give you, so everything in being between the orange brackets should equate to, so we still have a series combination of cable 3 and motor 1. So everything in between the orange brackets, square brackets should give you um, 0.049169 plus J 0.440898265. That is what all this chunk simplifies to. So that will be 0.14182539 plus J 0.41565179875. And to get the magnitude of this, the polar representation of that will be 0.41802 at an angle 83.8971 degrees. And therefore, our fault current will be 100 MVA divided by square root 3 multiplied by the voltage 6.6 and by the magnitude of our fault current, which is 0.41802, and that should give you 20.927 kA. 20.972 kA. Let me quickly calculate 26. Just a second. Just to confirm something. Yes, so that's it. Focus on yeah, 20.927. So yeah, that's what I had to go through. It's so when I think that's the fun of the calculations. It can get a bit complicated with the brackets, but if we just also sit and confirm, that should get you this answer. And so we'll jump to ETAP and then model this scenario and confirm our hand calculations. Okay, now we're in ETAP and this was our last scenario. So now we'll go back to connect the rest of our model, right? The rest of our model. And oh, mind you, the number of of conductors per phase 3, and that is also from our last video, right? Now we'll go on to run our short circuit study. Okay, we connected the rest of the network, and then we'll fault pass the unit board pass, which is what we just analyzed with our hand calculations. So when we run the short circuit study, should give us 20.927, and that is approximately what we have here. It is 20.926. It is giving us 20.926, which is very much within what we expect from our hand calculations. And again, this branch does not contribute anything because this branch has no voltage source behind the impedance, hence why nothing is being contributed by this branch. Same as the other branch where our low voltage unit transformers are not loaded. So that is that. In conclusion, our calculations match our ETAP model. So thank you so much for joining me in this video. Hope you join me in the next coming videos. Thank you.